on to the next session. So if you have any more questions, you can always send us an email and we'll be happy to answer.
Bhanuka, you're not audible. Can you try reshare?
Hello, Kidmin. Can you hear me?
I can hear you now, Bhanuka. Okay,
Okay.
you can continue.
Please let me know if my bandwidth is low. I hope it's okay now. So in this session, I will be giving an introduction to ROS navigation. I saw there were some questions regarding like Turtlebot navigation and whether we can do a small demo on navigation. Yeah, we can do that. We can do that in this section. So I'll be giving an introduction to ROS navigation and what are the important terms associated with that and how the ROS framework actually supports in ROS navigation problems. So because ROS navigation is somewhat a tricky example to discuss in detail, I'll be using analogy which is a navigation problem. So first, let's assume that you are a tourist and you need to go from Colombo to Kandy. You are somewhere around Colombo and you need to go to Kandy. So there are two ways you can do that. The first way is you behave like a full autonomous system. So first you'll need a map. So luckily Google Maps has already done that. And first you need to know where you are on the map. That is also called as localization. Uh, for example, if you don't know where exactly you are in Colombo, so if you assume you are here, but you're actually here, you might take wrong directions and you might end up cycling inside Colombo, but not getting into Kandy. And finally, you need navigation information, how to turn at each junction. Also, we call that as path planning. So you need a proper path to go get from Colombo to Kandy. So that is the first method. And the second method is if you have a local guide, that means you are not a fully autonomous system and you have a local guide and he will tell you how to turn at each junction. So you can just follow his commands and achieve the navigation task. Okay, now to do the second one as a semi-autonomous system, we'll see a demo later. And in navigation, there are basically three terms that you should keep in mind. First one is the mapping, which is the creating of the map of the environment. And localization, as I mentioned before, is the current position estimation in the map. And finally, path planning is like creating a path to the goal from your initial position. So in our tourist example, you will be operating around here. So you'll have to do the path planning as well as localizing, but you don't need to create a map because you already have a map. So there were some questions about SLAM in this slide link. So the SLAM will be here. So you will be doing the mapping as well as localizing both at the same time. In our example, we'll be doing here and we'll be using Google Maps. So ROS-based manual navigation. So if you are doing manual navigation, how you can do that in ROS? So it is like taking commands and just following. So how you can give the commands. So in order to demonstrate that, we'll using a Turtlebot 3 simulation. If you have the Turtlebot real robot, you can apply exactly the same algorithms there. And in this one, we'll be using the simulation. There are two Turtlebot robots and Burger and Wop. And to control the Turtlebot robot, we'll be using the keyboard controllers. So this is how it happens here. Yeah, in a ROS environment. So you'll have a node, a ROS node where it will be taking inputs from your keyboard and convert it into command values as linear velocity and angular velocity. So you need to give that command. So this is already available. You don't have to do anything. You can just run this node. And in order to give that information into the gazebo, if you have the real robot into that real robot, you need to publish it as a topic, and it is also done as standard using this command velocity topic. CMD well, and in that topic there are 6 terms. So linear XYZ commands, angular XYZ commands, and right now we have angular Z 0, -0, -2 command. Now it's a linear command. So now you can see the robot is moving linearly. Okay, so we assume that you are using a semi-autonomous method, but if you're going to if you're going like fully autonomous, so if you don't have the map already available, you need to create the map using some ROS tools. So if you are doing a robotics project, there's a highly likely chance that you don't already have the map, and this is a simulated gazebo environment. So these are like walls, and these white ones are like obstacles, and here you can see the robot is there. So in order to do the mapping, we can use G mapping or grid mapping package that is already available in ROS. So all you have to do is run the G mapping node using proper initial values and configuration values. And because this Turtlebot robot has a 360-degree laser scan, that means it can see the 360 surrounding and map into like a laser scan map in its 360 surrounding. It can create an immediate map, and as you can navigate your robot in this simulated environment, or if you have the real robot in the real environment, the RViz will create the map. It will attach all the map, all the details, and fill this map, and will create you the map. So you can use that map. So we can use that map later to do further navigation problems, localization problems, anything like that. So if you are like getting into ROS navigation, so you understand now what is localization. So that localization is estimating your current position in a map. And there's always something called uncertainty associated with localization. So every time you define mathematical terms or anything, there's some uncertainty. So in order to describe that, let's assume that you are going on a road trip and you were sleeping, and now you are suddenly asked to drive the vehicle. So this is what you see. So you can see a big long road, but you can't see any landmarks or anything. But let's assume you have a map. So in that map, you need to localize yourself. You also know where you need to go. That means you know your goal, where your goal is. But from this information, you cannot be sure whether you're 100 kilometers away or just 1 kilometer away. That means you cannot localize yourself on the map. So if that problem happens, what you should do next, you can keep driving. And if you see some landmark like this, so it says 160 Nevada. So that can be something like 160 milepost. So with landmarks or mile markers, you can increase your confidence for where you are. But still, there can be some uncertainty left behind, because maybe someone has put this landmark in a wrong position, or maybe this is a fake one. So that is why there is always uncertainty. Even if you see any tutorial or anything like that, there will be that term uncertainty. So that is why there's uncertainty. And ROS navigation framework contains localization algorithms. You don't have to implement everything from scratch. So they are already available. So one example is called AMCL. If you know, it's adaptive Monte Carlo localization. You don't need to know exactly the internal algorithm. You can just use that if you have the correct framework. So this is a small demo. So this is the simulated world, and our robot is navigating in that world. So so these green markers, they represent the uncertainty. You don't have to go very much deep into what they mean. So it is like a representation of uncertainty. So as the robot sees other obstacles, and as it moves forward, it can increase its confidence about the environment. Now at the initial condition, there's a lot of uncertainty. Even it can be like here, even though what you see is different. So, but as you move on, you see these obstacles, and you can increase your confidence. So after some time, you are properly localized in your map. So now it is pretty much localized in this small area, and you can use this localized information and this map to do any other navigational task in future. So that is like the initial condition. So that is localization, and I hope you all got an idea about what that is. And the next term we need to discuss is wheel odometry. So this is also an important thing in while we discuss navigation. So if you are the tourist, let's say you are playing a Sri Lankan game, and you are blindfolded, but you need to go somewhere and do some draw something to win that game. So even though you are blindfolded, you can count your steps and move forward and achieve your navigational task. Just like that, even though the Turtlebot robot has a laser sensor here, let's assume that it is blindfolded. Okay, now it can see its environment. All it can do is approximate where it has gone using only the other information. That means how many turns the wheels have rotated. So we can count how many left wheel rotations, and we can count how many right wheel rotations. And from that, we can calculate the linear velocity as well as angular velocity. So if this is moving forward and this is moving backward, it will be taking a rotation on the spot. So that is already, the wheel odometry is already implemented in ROS environment. And in order to trigger that, according to your robot, you have to run a simple node. So it will count the left turns and right turns, and according to that, it will publish what is the linear velocity and angular velocity. So this is the information that is published into that topic. So that is a very easy thing you can do. So this is the real simulation. So this is how the robot navigates in the gazebo environment, or if you have the real robot in real environment. And all we have shown here is a wheel odometry based path. So it will get this odometry information, or the RVs will subscribe to the odometry topic. And you can see it has done a pretty good job in representing the trajectory of the real robot. So that means if there are no slipping or anything like that in the wheels, you can very easily use the wheel odometry information to navigate in ROS environment. So let's say, for example, like if the sensor is blocked for some scenario, then you only have to depend on this wheel odometry. So that is why it is very important. Okay, in the previous session, Kitmin mentioned about ROS transformations. So why that is important for ROS navigation. So let's discuss that using another example. So let's assume that you are a tourist from USA. So in USA, you have vehicles with left-hand drive configuration, but in Sri Lanka, we have right-hand drive. So how do you adapt to drive in Sri Lanka? So if you are used to drive in left-hand side, the way you see other traffic and the road, how you drive, everything is different. The way you see everything else in the environment is different. So how you can adapt? So if you are like if you are like flexible, if you are a flexible tourist, you can just jump into the right hand side and see the environment and like adjust yourself. So you can see, okay, this is how it's going to be. And like you can change yourself and drive or do the navigational problem in Sri Lanka or any other country in this world. But if you are not flexible, that means you are very strictly configured with transformations and coordinate frames, then you'll have to do a very hard things like changing the entire behavior of the car, like have mechanical things and so on. So this is not very good. So ROS is something like this. You can define the coordinate frames very easily, and if there's a rotation of if there's a change, the ROS will automatically track that for you. So this is like a very adaptive method, and it is called ROS transformations package and also known as ROS-TF. It is something like that. So your base laser scanner is here, but your base link is here. So if you see an obstacle at 0.3 distance from your laser scanner, what is the distance to that obstacle according to your base link? So this calculation is automatically handled using ROS. So what you have to do is initially you have to define the initial coordinate frames. And as the robot moves forward or does any navigational task, it will track the coordinate frames with respect to each other. So as you can see here, the robot is moving forward, the wheels are rotating, but still ROS is doing a pretty good job in handling the coordinate systems for us. So you don't have to write any algorithm, you don't have to do any kinematic operations. ROS is doing everything for you. All you have to do is define the initials. Okay. Next important topic, global and local path planning. So you'll definitely get across this one, and that you'll have to use this one if you are doing a ROS navigational task. So global planning is like this. It is like the very high level or the abstract navigational path of your robot, or in our example, in our tourist example, going from Colombo to Kandy. So it is like the Google Maps path. But you cannot just rely on that. So if you are in an environment like this, you cannot depend on this Google Maps data, but you have to depend on your ability to navigate this kind of a traffic. So how you should navigate not hitting any of these vehicles. So you might have to take right, you might have to change your lanes and adjust to traffic lights and so on. So global path planning is something that is shown here in the right hand side. So it will divide the grid into like small subgrids, and it will calculate from initial position here into target here what is the path it can take. So it will evaluate all the possible scenarios and it will take the first one, and there are so many algorithms related to that. So ROS can do the global path planning, as well as there should be a local path planner associated with your robot as well, because it should be able to handle the immediate environment as well. So that is global and local path planning. I hope you got the idea. And this is a small demo for the same Turtlebot robot. So the Turtlebot robot, it was here around somewhere here, and we have given a navigational task to go here. So we have given the final position it needs to go and the orientation. So this, if you can see here, this black line is the global path plan, and this yellow line is the local path plan. And it is not up to the final point. It is like a very immediate one, the yellow line or the local path plan. So the ROS will handle everything, and you don't have to do any algorithms. You can just use the available global and local path planners available in ROS. Then finally, there's something called a cost map. So we can explain it like here. So I have shown in red the vehicles on the road. So if you hit them, it will cost a lot for repairs. So that is the basic idea of a cost map. So even in ROS environment, you can see, so there is a high cost near obstacles, and always ROS will take the path, ROS will derive the global path along this blue line where there's little cost to navigate. So using a method like this, it ensures that you won't be hitting any obstacles. And this has done a pretty good job. If you see videos available online, it can handle dynamic environments, people falling in front of the robots, they can handle very well. So I have explained so many like examples and like small parts that are associated with ROS navigation. Now, if you gather all of these and put into a chart, we have the ROS navigation stack. So I hope whenever you see the ROS navigation stack, you can understand what happens at each place. So we have the global plan and local planner, as we mentioned before, and we have a local cost map and a global cost map. So global cost map is like if you have two paths, whether you can take the highway or the normal road. So in highway you'll have tolls, but it will take a small time, and if you take the normal route, it will take you more time, but it won't cost you anything like that. So there will be like global cost map, local cost map, and if you have a map available, you can include that into this navigation stack. So the ROS can localize itself in that map using nodes like AMCL. So AMCL is a localization map, localization algorithm. And if the sensor sources you have, you'll have only thing you have to do is like have it publish the information in a correct ROS topic. If it is usually all these sensor source manufacturers provide ROS libraries, so you don't have to worry about anything, just run the node. And likewise, odometry source, sensor transformation. So this is the transformations I mentioned earlier. So you'll have to define that and give into this navigation stack. You can easily do that. And odometry source assessment. And this base control is something like how you control your robot. So it's something like whether you are driving a manual vehicle or automatic vehicle, the way you drive the vehicle should be different. So you'll have to give how you are going to give the commands, whether you are only using how you shift gears, likewise. So this is the ROS navigation stack. Hope you guys understood that. So in this section, I used a Turtlebot 3 simulation to discuss everything. So this is very easy to set up and install. So all of you can try this at your own pace later. So either you can have your own Ubuntu and ROS version in your machine, or you can use an online platform like Constructzy. Then all you have to do is install some ROS packages. So there you can see like AMCL, that is the localization package, and install packages like that. And then install Gazebo ROS controllers. You can do this from lines, some simple lines, and all other things, how to this Robot IS website 3, and you'll get all this information. I'll be answering. Thank you very much.